Hey everyone, how you doing today? So I'm Philip from Baseten, and I'm going to be talking about inference optimization. I call it like the golden triangle. It's the opposite of the Bermuda Triangle. Golden triangle of inference optimization, balancing latency, throughput, and quality. So a little bit of introduction. I lead developer relations at Baseten. Baseten is a model inference platform. I'm based in San Francisco, and yes, that does mean that at 11 o'clock Pacific time last night, I got on a red eye, flew here, got to the airport at 7 a.m. and came straight here. That's how excited I am to talk to you guys. I'm a martial artist, avid reader, I'm an author, and I absolutely love talking about model performance optimization. So what's our agenda for today? We're going to talk about two things, tools and techniques. We're going to do a quick overview of GPUs and fast inference frameworks, and then we're going to dive into all of the different model performance techniques and their trade-offs. Because our whole talk is about trade-offs. We're trying to balance latency, throughput, and quality. And as you can see here, one out-of-order slide from the midnight slide review on the plane. We are going to be mostly limiting our scope today to LLMs because LLM-based architecture is actually really common across modalities. All of the stuff that I'm going to talk about today for language models also applies when we're talking about optimizing stuff like Whisper, speech synthesis models like Orpheus, embeddings, re-rankers, classifiers, and sometimes even image and video models, although those can have pretty different architectures in some cases. So anyway, here's the big triangle. We've got throughput, we've got quality, we've got latency. This is not a new problem for AI engineering. If you've ever heard the idea of good, cheap, fast, pick two, it's exactly that. We've seen this before in, for example, game engines, graphic rendering. You can render something very high detail, but is that going to render, with a high frames per second? And are you going to need to buy an expensive GPU to do that? It's exactly the same concept, just for LLM optimization. So our goal in this talk today is to understand the multidimensional optimization space of model performance and identify which techniques fit which circumstances. Let's take a quick look at the tools we're going to be working with. First off, we have GPUs. GPUs are amazing. They're these throughput machines that we want to take full advantage of. We want to make sure that we're completely utilizing the available VRAM, the compute, the partitioning that we have access to. We want to make sure we're effectively using the GPU to GPU interconnect so that we can leverage more than one card or even more than one node at a time. And we want to make sure we're effectively leveraging the GPU to CPU interconnect so when we don't have to use these scarce GPU resources, we're not going to. The other thing that we're going to have access to today is something called a fast inference framework. So if you go on like Hugging Face and you look at a new model and you scroll down in the model card and you see a code sample, usually it starts with import transformers and then you just run the model like that. That's a great way to get started out of the box, but for production use cases, this is not going to be fast enough. You're going to need to replace that with an optimized inference server. So some popular frameworks are VLLM. This is like the most popular one. It supports almost every model and lots of different hardware, including now TPUs. But it's not necessarily always the fastest. SGLang is a newer one. It's highly customizable and has amazing performance, especially on DeepSeek and Qwen models with support for a lot of new inference techniques. But it's not as widely known. And then TensorRT LLM provides the absolute best performance on NVIDIA GPUs, but it can be kind of a pain to work with. So no matter which framework you're using, you're going to get better performance than just transformers out of the box. But we're going to want to, make sure that every technique we talk about here is covered in the framework that you're using. And one question I actually get a lot is how do these frameworks fit into the model serving stack? So if you look at, this entire, this box here is the model pod. This is maybe your Kubernetes pod. You have the actual fast inference framework is a small box within the back end of the model server that's handling, inference, batching, LoRa swapping, logic processing, that kind of stuff. That's generally going to use a gRPC connection to a sort of front-end model server, which is going to handle the formatting, the schema adherence, all that kind of stuff. So these fast inference frameworks are not model servers in themselves. They're pluggable components into model servers where you're going to be able to, swap them in and out depending on which model and which feature support you need. So, techniques. What do we want? We want low latency, we want high throughput, and we want production readiness. We want it to be as fast as possible, as cheap as possible, and as good as possible. So what's stopping us? What's stopping us from getting these goals? The main constraints we're going to deal with are, number one, compute and bandwidth. Where is the bottleneck? Are we bottlenecked on compute and prefill? Are we held back by how quickly our GPUs can do optimization? Or are we bottlenecked on bandwidth for decode? Little hint, usually we're going to be bottlenecked on bandwidth. VRAM bandwidth in terms of how quickly we can load those weights and activations out of memory. We're also going to be constrained a little bit by the nature of our traffic. If we have low or inconsistent traffic, there's going to be a lot of stuff that just isn't going to make sense for us to do from a cost perspective. We're also going to be constrained on stuff like sequence links and also prompt and subject matter, because for some optimizations, it actually matters what the contents of the requests are. We also have to keep in mind feature compatibility. For example, if we're trying to do a lot of KV cache reuse and we're also trying to process very large batches, those are both competing for this limited VRAM. So we have to, keep in mind as we consider these optimizations where they do and don't work together. We get to choose which hardware we're going to use, we get to choose what tools we're going to use, but ultimately we do have to fit our workflow to the hardware. There are these fundamental limitations. So let's start with some of the easy ones. Let's look at improving latency and throughput if, on the other side of the triangle, you're not quite so concerned with model quality. So you'll see here, in all of these slides, I've got this little triangle. And if the text is in white, that means it's something that we're focusing on with this technique. If it's in green, that means it's maybe going to be either held the same or slightly sacrificed in pursuit of these other goals. So the number one thing, obviously, that you can do for performance is model selection. If you benchmark and evaluate, say, Llama 8B, and it turns out that it works just as well as Llama 70B for what you're trying to build, you've got a huge free win right there, in that you're just serving a much, much smaller model. So not really a model performance technique, but it's always something I like to bring up. Obviously, just start with the best frontier model when you're prototyping. But when you launch, see if you can do some evals. See if you can just use a smaller model. A more specialized version of model selection is distillation, which is where we're trying to express the same model characteristics with fewer parameters. In distillation, you use a large teacher model to either train new LLMs from scratch, or more common these days, fine-tune existing smaller LLMs like the DeepSeek R1 distills. The difference between this and ordinary fine-tuning is you're not just training it on the outputs, you're actually teaching the smaller model how to mimic the probability distributions of the larger model. So if you have, a very large model that you're trying to serve, like this DeepSeek R1 model, 671 billion parameters, and if you can, squeeze that into 70 billion parameters by distilling it into a Llama 3.3 base like DeepSeek did, there's a, 10x reduction in every single problem that you're trying to solve on the model performance side, just kind of for free out of the box, if the quality hit is something that your application is okay with. And then another way of shrinking these models is, of course, quantization. So smaller number formats require less bandwidth. Again, we're almost always bandwidth constrained, and unlock more flops. At Baseten, we're huge fans of using FP8. We never really served customer workloads back when it was only int8, int4 on quantized, using quantized weights, because generally the quality hit was atrocious. But today with FP8, which is supported on Lovelace and Hopper and Blackwell GPUs, we're seeing a very high dynamic range with this number format that preserves quality. We're even able to use it to quantize stuff like KV cache. And we are testing FP4 today on Blackwell. It's still kind of up in the air whether or not we're going to be serving a lot of workloads with that. One quick note, when I say high dynamic range, why FP8 is better. So if you look at FP16, sometimes it's bfloat 16, but they're very similar number formats, 16-bit number formats with 5 exponent bits. This allows a wide range in your numbers that are used to express your model weights. When you go to int8, you have no more exponents. But with FP8, you still have 4 of those exponent numbers. You're only losing 1 bit of exponents. Because of that, you're able to express a much larger dynamic range, which captures the weights a little better. So let's say, you can't do any of those. We're stuck with the model that we have. We've got to use the number format that we've picked out. We can't distill it. We can't quantize it. We can't pick a different model because for our use case, we have to serve the absolute best model. What can we do next? So let's focus instead on preserving quality while having great throughput, making sure we're able to, serve a large volume of traffic very cost effectively. The number one thing that's going to help here is batch inference. And this is a big trade-off decision that you have to make between, latency and throughput. Our goal when we're batching is to make these memory-bound operations instead of compute-bound. Again, we're almost always going to be limited by how quickly we can read off of VRAM. So if we can do more compute cycles per VRAM read, we're going to be using our hardware more efficiently. So the key consideration here, the trade-off though, is that as these batch sizes increase, our time to first token is also going to increase. So when we do benchmarks, we generally run benchmarks on all different batch sizes, 1, 2, 4, 6, 8, 16, 32, 64, 128, and we're able to draw a sort of trade-off curve between the total tokens produced and that time to first token, and then give it to the customer, say, hey, here are your options. What makes sense in terms of this, price to performance trade-off. When we're also batching, we have to, do some capacity planning to make sure that we're going to leave enough memory left over for all these other optimizations we want to run, like speculative decoding and expert parallelism. So when we are batching, this is going to be standard with basically every framework, TensorRT, LLM, etc. We do always want to make sure we're doing in-flight batching where the requests are at a token level, swapped in and out. We do not want the overhead of dynamic batching or worse, individual requests. Another great throughput optimizer is disaggregated serving. This can help with latency, but that's not the main goal. The main goal is to use different hardware for prefill, which is this compute-bound step, and decode, which is this memory bandwidth-bound step. For example, H100 and H200 GPUs have equivalent compute profiles, but H100s are a lot cheaper. So if you can run prefill on those, and you can run decode on the H200s with their 40% higher memory bandwidth, then you're able to get more throughput out of the same hardware than if you just ran both parts of the inference step on both pieces of hardware. It also lets you scale prefill and decode independently, which helps when you're setting up like very, very massive pipelines. But let's say, it's great. We've got a good model, we've got high quality, we've got high throughput, we can serve our production traffic. But honestly, no one really cares about that. What people care about is we want the models to go fast. We want to be number one on artificial analysis. We want to, make some pretty screenshots of our benchmarks and put them on Twitter and show that our number is higher than everyone else's. How do we do that? How do we get our latency down? So there's a few different challenges in making sure that your latency is as low as possible. One big one is this long context handling. With Llama 4 Scout, for example, we now have a 10 million token context window. Whether or not we can do anything with it, that's another story. But at least, for today, what I'm just concerned about is, okay, how quickly can we process those tokens, whether or not the results are of any use. So one important default is to switch on chunked prefill. Another huge one for long context handling is to switch to max utilization so that we can make sure that every single block of context is going to be loaded into memory. And there are a lot of new techniques that are coming out all the time for this. DeepSeek, for example, released a really high quality MLA implementation that's reducing by about 93% the amount of KV cache that's needed to load this long context. So as these new models are coming out, also new techniques are coming out to handle this. But, another thing, after that prefill step, we have the actual decode step. And that's where speculation or speculative decoding can be really, really useful. So as I've said like 10 times up here, we are bound on memory bandwidth. We are trying to make the most of every time we read these weights from VRAM. So what if every time we read the weights, instead of making one token, we could make multiple tokens? That's the basic premise of speculative decoding, and that's why it's so great for latency. We're trying to generate multiple tokens per forward pass. The most basic form of speculative decoding is draft target, where we have a small model that makes draft tokens, and then a larger model that validates them. We also have different techniques like Medusa and Eagle that can modify the target model directly in order to have it generate multiple tokens. But in almost all cases, speculative decoding performance is going to depend on the draft token acceptance rate. And that's why it actually depends a lot, unlike all of these other techniques, on the actual content of your requests. A draft model might do really well on certain things like code generation. That's very straightforward. We use speculative decoding for accelerating code generation a lot. But for something like, I don't know, writing poetry that's a lot less predictable, the draft model might not do particularly well. So we want to make sure that we're constraining our speculative decoding to domains where it actually makes sense to run. As a quick example of how speculative decoding actually works, we have these input tokens, and let's say that our draft model, the small model, comes up with A, B, E, D to continue this pattern. The target model, the larger model, is going to take a look at those draft tokens and either accept or reject them. So let's say it says A and B are correct, but E is wrong. As soon as it gets to one wrong token, it throws everything else away. But these two correct tokens become what's called the prefix, which is sent into the next forward pass of the target model. It generates one additional token C, and we get these three outputs A, B, C for a single forward pass. So basically, in this example, we got 3 tokens for the price of 1. And speaking of 3-in-1 optimizations, I actually had thought about calling this section free lunches. It's not actually free. Nothing in model performance optimization is free. The catch here is you need to have a lot of traffic for this stuff to make sense, because you're spending a lot of money on hardware to make all this stuff work. But the upside is, if you do have that traffic on a per request or per token basis, you're going to be a lot faster and you're going to be spending a lot less money. So what are these rare 3-in-1 optimizations, these things that help with throughput and latency while retaining quality? Number 1 is KV cache reuse. You should basically always be using this. You save latency on every cache hit, and it lets you support really long prompts. One question that's constantly going around is like, is RAG dead? We can tell from all the talks here that it's not. But the sort of counter argument is, well, if I can just load my entire context into the model every single time and hit a cache on prefill so that I don't have to recompute everything, well, it's just free to pass my entire context in. Not 100% the case, but it is true that as long as we're able to, have a pretty high hit rate and share a system prompt or context across queries, especially if we're able to, at the infrastructure level, route to the actual appropriate model server, depending on, previous context, to make sure that we're having an especially high hit rate, then we can actually get really great performance on this time to first token step for these very long context problems. We also have the option in many cases of offloading this KV cache either onto CPU RAM, especially for gray style systems where there's very high bandwidth between the two of them, or if you're using a sort of shared memory layer underneath all of your GPUs, you can store all of your KV cache there. So I think that, as you're looking at model performance optimization, especially from an infrastructure angle, KV cache reuse, it's one of those big 3-in-1 optimizations and is a great place to spend a lot of time. The other big one is parallelism, which probably should have gone very early in the talk because it's such a fundamental topic, but it is very important as this 3-in-1 optimization where we're splitting inference load across GPUs. And again, the catch here, you need the traffic to justify the cost of these GPUs, because I'm about to show you systems that cost as much as like hundreds of dollars per hour to operate. So with these, you have a few types of parallelism. You have pipeline parallelism, which is where we don't generally recommend this. It's where you split the layers across the GPUs and run through them sequentially. What we generally prefer is either tensor parallelism, expert parallelism, or context parallelism. To touch on context parallelism really quickly, it's the idea that you kind of split your context of your requests across multiple GPUs. It can be useful in these long context situations, but most of the time we're talking about either tensor or expert. To look at a breakdown between the two of them, in tensor parallelism, the model weights sit across all GPUs. And this is good because it lets you use all of the compute and all of the memory resources of these GPUs to serve all of your requests in batch. But increasingly, models are not just a single big blob of weights. They're a mixture of experts models. This is a increasingly popular architecture. We saw DeepSeek v3 and R1 use this. We see the new Llama 4 models use it. I'd be willing to bet, I don't know, but I'd be willing to bet that Quen is going to use it in its next release. It's just where the industry's going. So with expert parallelism, it's a really cool technique where you take each expert and you put whole experts in each GPU. One GPU might have 4 experts, 1 expert, 16 experts, but each expert is going to be stored entirely within a single GPU. And with this, you're able to get really exceptional performance on mixture of expert models, especially with the other fun optimization, which is multi-node inference. So multi-node inference introduces a new challenge to the performance optimization around parallelism, because you're going from, okay, I have 8 GPUs in a single node with very high bandwidth interconnect between them, to now I have multiple nodes, I have a much lower bandwidth connection, and now the hardware topology is actually going to affect my parallelism strategy. Expert parallelism requires very little communication between GPUs as each expert resides independently. And because of that, it's a great option for multi-node inference. So if you want to take, DeepSeek R1 and make it really cook, you get a couple nodes of B200 loaded up on there, or, with Llama 4 Behemoth, when that comes out, that's going to be 2 trillion parameters. You're probably going to need to do this even with B200. And it is going to be absolutely blazing fast, even for very, very high volumes of traffic. Again, very expensive to, spin up multiple nodes of hardware, connect them just to run a single model. But once you're serving tokens at a high enough scale, it's going to be cheaper on a per token basis. So in summary, on hardware, GPUs are throughput machines, but we need to build our optimizations around their limits. We want to make sure we're appropriately trading off between latency, throughput, and quality, and use the huge range of techniques that are available on the market today to give us the options we need to reach our goals. Thank you so much. Definitely feel free to hit me up on Twitter and LinkedIn, and I will be around. I've only got 2 minutes left on stage, but I'll be around out there all day to answer any questions that you have. Thank you so much.
Baseten just focused on LLMs, or is it more use cases?
And thank you for giving me an opportunity to show my employer who paid for my plane trip over here. We serve every model: LLMs, embeddings, Whisper, TTS, image models, video models, and I would be happy to give you a little demo or something.
Other than privacy reasons, do you see a reason for a company to do their own first-party inference right now, given that, Together is subsidizing every token we generate?
Yeah, so that's the classic shared inference versus dedicated deployment. A big one is reliability. If you look at the uptime of, say, a shared inference endpoint, it generally looks a bit like a Christmas tree. If you're doing mission critical workloads, you cannot have spikes in your P99s and you cannot have downtime. So that's a really big reason to do a dedicated deployment, whether that's something that you're using a platform like Baseten for, or you're just spinning up some GPUs on GKE yourself and loading them up with VLLM. So yeah, it is privacy. That's a small aspect of it, and compliance, that kind of stuff. But it's more around reliability, performance, customization, that kind of stuff.
One last question. All right, Phil, where again can they find you?
They can find me right here on Twitter and LinkedIn, and they can go on Baseten and read like 100,000 words that I've written on this topic. So yeah, please come through.